Okay, this will be the lecture for Chapter 29, and we'll be talking about light waves. Now, I do have some good news for this chapter. There's no equations in it, and it's relatively short. So I'm going to talk about how light can have this property called polarization. I'll talk about why we have polarized sunglasses. I'll talk about how light propagates. I'll talk about something called Huygens principle, which is related to the propagation of light waves. I'll talk about what happens when light hits an obstacle. It turns out that it can bend around it, or it can diffract. And light waves are like mechanical waves in that they can superimpose. They can live at the same place at the same time, and they can interfere with each other. They can constructively interfere, in which case, in the language of light waves, it would be a bright spot. They can destructively interfere, and in the language of light waves, they can cause a dark spot. Now, one property of light waves is going to be something called polarization, and what it's really related to is how we wiggle our electrons. Kind of what I said was, suppose I had an electron right here, and I wiggled this electron up in the vertical, and I wiggled this electron down in the vertical. Then you could convince yourself that my electric field would be going up and down because it follows the electron. And it turns out, for reasons that you don't know about and that you don't care about, the magnetic field is going to be perpendicular to it. Really, we only care about the electric field when we talk about polarization because it's conceptually easy to think about wiggling electrons. Now, my light wave would actually travel in this direction right here, and I would actually say that this light wave is going to be polarized, and it's going to be polarized in the vertical. So the electric field is going up and down in the vertical. If I were to kind of be an observer right here, and if I were to look at this thing, then I might see this light wave coming at me, and I might draw the electric field kind of going up and down. So looking at this thing head on, I would say that this thing is vertically polarized. However, suppose I were to take my electron and not shake it up and down in the vertical, but maybe now shake it horizontally. So shake it this way and shake it that way. Well, my electric field wouldn't be going up and down anymore. It would be going side to side, and my magnetic field would be going up and down. So if I were to look at this thing head on, I would say that my electric field is kind of going in the side to side direction. And I would say this thing is actually going to be horizontally polarized. Now, you can shake it any which way you want, but we can also say what happens if the electrons are going in every direction. Say something like the sun, right? The sun is going to have lots of electrons, and these things are wiggling in pretty much every direction. We're going to have some in the vertical, we're going to have some in the horizontal, and we're going to have some in every angle kind of in between. So this type of light isn't going to have some preferential polarization. It's going to be what we would call unpolarized light, and essentially the vibrations are pretty much random. Most of the light that we're looking at is going to be unpolarized light because light sources like the sun or lights, they tend to be random. Now, what we can actually do is we can introduce something called a polarizer, which is essentially going to be a piece of glass or plastic, and it's only going to let certain polarizations of light go through it. Hence, polarized sunglasses. They're only going to let some polarizations in, and I'll talk about those in a little bit. I don't know how we make these pieces of glass or plastic, but I can tell you that they only let certain polarizations go through them. And we generally talk about the horizontal and vertical components because we can build any component outside of that. Suppose I had a light source, and this is a flashlight. It's going to be unpolarized. So see my unpolarized light right here. What's going to happen is, suppose I had a vertical polarizer. This vertical polarizer is only going to let the vertical components kind of come through, the up and down components. What comes out of this guy is just going to be light that has a vertical polarization through it. This would be like taking a rope and then shaking it through a pallet or something like that. We can only let the rope that's shaking up and down go through that pallet. If we were to pass through a second pallet, as long as that pallet was oriented in the vertical direction, then the rope's going to go through it. The light would also go through it. Now, suppose I had a polarizer right here that let vertically polarized light go through it, and then I had a horizontally polarized polarizer right here. So I'm going to take my unpolarized light right here, send it on through it. This one lets my up-down go through it. This one lets my side-to-side go through it. There's not going to be any light coming through the side because we've taken out the horizontal here, we've taken out the vertical right here. We're not going to see any light. This would be like taking a rope, shaking it up and down, going through a vertical pallet, and then putting a horizontal pallet right here. You can see that this light right here isn't shaken, and essentially what that means is we're not going to see any light. Here we've gotten rid of the horizontal. Here we've gotten rid of the vertical with my vertical and horizontal polarizers, so we're not seeing any light. Now, let's go ahead and take a look at an application of this. Here we have a lady, and this lady has two polarizers. Let's just, for the sake of argument, say that this guy right here is a vertical polarizer, and this one right here is a vertical polarizer. You can kind of see that we're going to see less light coming off of this lady because the polarizer is going to take away some of the light that's reflected off of her. And this one right here isn't going to take away any more. Now, if I were to have the same setup where this is going to be my vertical polarizer, if she were to turn this thing such that it's letting the side to side through, you can see right over here that it's going to be dark. And what's going to happen is this guy takes out the vertical, this guy takes out the horizontal, and what makes it through is absolutely nothing. Now, kind of an application of this, let's just talk about why we wear polarized sunglasses, especially if we're on the water. So this is going to be my water, and if I had some light kind of coming in, and it was vertically, or it was unpolarized, then what's going to happen when it bounces off of a surface, when it reflects, it's actually going to partially polarize it. And really it depends on what angle it's coming in. Now, this does have implications. If I were to think about sunlight for a second, sunlight is going to be unpolarized. So here we have our sun, and the sun is, kind of going in the all directions. All directions that we have. When light comes off of water, we have glare. Glare is mostly horizontal polarization. So what we have is we have lots of horizontal polarization, not a lot of vertical polarization. Now, if we were to get a pair of polarized sunglasses, what we want to do is we want to get rid of that glare. So what we do is we put in a vertical polarizer right here, and what makes it through is not the glare. What we see is just going to be the vertical polarization. These guys still do get rid of some light, and if we were to look directly at the sun, we're not going to see the side-to-side components, we're just going to see the up and down components. Our eyeballs are not sensitive to polarization. We want to get rid of the glare. This image right here kind of shows what a polarizer does, and actually it's showing it for a camera. Here we have our camera. You take a picture of the water, looks pretty bad. If you take the Simpsons photography class, then they'll tell you use a polarizer, and this is the before, this is the after, and I don't know about you all, but this one looks prettier. Now, really quickly, I want to answer the age-old question, how come I can't read my iPhone when I have my polarized sunglasses on? Well, any LCD screen, what we're going to do is we're going to have a backlight, and we're going to have a liquid crystal display, LCD, and what's going to happen is this thing forms the image by messing around with the voltage. The very last thing on any LCD screen is a polarizer, because this thing only makes the image in one polarization. So what it has to do is it has to get rid of the other polarizations because our eyeballs are not sensitive to it. If I were to try to view this thing with some sunglasses on, then if they're in the same polarization as the polarizer, great. If they're in the opposite polarization, you're just going to see a dark screen. Now, I kind of want to change gears a little bit, and I'm done with polarization. Now I want to move on to the rest of the chapter, and I want to talk about how light can actually propagate. And this is going to be important when we talk about interference, and more specifically diffraction. Suppose I had a wave crest, and this wave crest at some time was this line right here. We could say that the light ray is traveling in this direction right here. It's always going to be perpendicular to the crests. This fellow came along, and his name was Huygens, and what he did was, around the 1600s or so, he said, let me take this wavefront, and I can take this wavefront and I can break it up into little teeny tiny pieces. And each one of those pieces is going to act like like its own source. And we know that sources are going to put out spherical waves. If I were to take a rock and drop it down into, say, some water, I know that the water is going to go out in little teeny tiny rings. What he said was, this wavefront, I've sliced and diced it up into little teeny tiny pieces, and this is going to be a source, 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 and right here. That's like dropping in a rock here, and here, and here, and here, and here. these guys are all going to send out spherical waves. At some later time t, these guys are all going to live at the same place and at the same time, and I'm going to have a new wavefront that's going to live right here. And essentially, the speed of propagation is going to be equal to the speed of the waves. That's what Huygens' principle really boils down to. Now, this just kind of shows pretty much the same thing. If I were to take a rock and drop it down in the water, we know that it's going to send out spherical waves, so right here, and then right here, and so on and so forth. Essentially, what Huygens said was we take this thing right here, it's definitely going to look like a point source. It's going to put out rings, if you will. This little piece right here, I can take this wavefront and I can break it up, slice, 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 and dice. Each one of these guys is like dropping in a rock here, and here, and here, and here, and here, and here. At some later time, all these guys add up, so we're going to get a wave, and a wave, and a wave. So taking a wavefront and breaking it up into tiny wavefronts, if you will, is simply called Huygens' principle. Now, this just kind of shows that rock being dropped in the water, only this is kind of a top-down view. So here's where I dropped the rock in, and it's sending out waves, so this would be the wavefront that I kind of indicate. And again, what Huygens said was you take this thing, you slice it up into this chunk, and so on and so forth, and you treat this like a source, and 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 so on and so forth. This thing is going to send out spherical waves, and at some later time, it's going to look like that. This one's going to do the same. It's going to look like that. This one's going to do the same. It's going to look like this. And all these guys are going to add up such that we get a new wavefront at some later time right out here. And what we have is we're going to have the propagation of our wave. Let's just talk about an application of Huygens' principle. Suppose I had a water tank like this, and we have a girl that's messing around with the water. She's pushing a board back and forth, and she's sending out some plane waves. And what we're going to do is we're going to mess around with how big this opening is. This is for water waves, but it actually works for light waves as well. So here we have our wave crests kind of coming into the opening, and what Huygens said is we can take this thing and we can slice it up, dice it up into teeny tiny pieces. So this is going to act like a source, and this is going to act like a source, and this, and this. Now, what's going to happen is these guys are going to act like sources, and you can see it would look kind of like that, and like that, and like that, and like that. What this boils down to is the wavefronts are actually going to fan out, as you're seeing right here, because we're seeing the propagation of 1, 2, 3, 4 sources that are acting like, so they're sending out spherical waves. As we make this thing more narrow, then maybe we're only going to have 2 slices and dices. And what we can kind of see is it's still going to fan out. So this one's going to send out waves, and that one's going to send out waves, and it's going to look more like a sphere, if you will. So it's going to bend it more. Now, if I were to make this opening teeny tiny, then I might only have one source, so you can see that this is acting just like dropping a rock in the water. And what we're going to have is we're going to have a nice clear pattern that looks like we dropped a rock in the water. Now, kind of some applications for this is going to be cameras. If we wanted a camera to have a nice clear image, then we would use a small opening. So you see how clear this guy is? It has a small opening. It doesn't let a lot of light in, but it makes a very clear image. If we were to have an opening that was really, really, really big, you can kind of see that this guy right here is going to be relatively, fuzzy, for lack of a better word. And the same is true for cameras. If you have a big opening, you let lots of light through, but it's not nearly as clear.